This is the second block of Topic 19. In this one, we're going to explore 3 more investigations relating to a radius of a circle that's bisecting a chord and having congruent chords on a circle because they intercept congruent arcs or they are equidistant from the center. So still looking at some relationships with chords today. This is a review from your last lesson, 19.1, of the conjecture that we made based on that investigation. So remember, the conjecture said that the perpendicular bisector of a chord on a circle will always contain the center of the circle. So that is a way that you can find the center of a circle. If you don't have it, you can draw 2 chords, find the perpendicular bisector of both chords, and where they intersect would have to be your center. So we talked about why that conjecture was true. We proved it, and it was because we knew dA and dB were equal, and dB and dC were equal. So remember, when we learned about perpendicular bisectors, we said every single point on a perpendicular bisector is equidistant from the 2 endpoints. And so because the perpendicular bisector contains all points equidistant from the endpoints, that's how we know dA, dB, and dC are all equal. We also know point D is the center of the circle containing points A, B, and C by the definition of a circle. So since we know from the center to this point on the circle is equal to the center to this point on the circle is equal to the center to this point on the circle, those are all radii of the circle. And so that's how we know point D is the center. All right, so let's look at questions 1 and 2 in your notes. This is our second investigation. Investigation 1, remember we found the center by drawing perpendicular bisectors of 2 chords. But in this investigation, we're going to know the center of the circle. So we're going to learn what can we conclude about a radius bisecting a chord or is drawn perpendicular to a chord. So let's look at this animation. So in circle C, we have chord AB that has been drawn and located its midpoint. So point M is the midpoint of segment AB, the point that's in the middle. We're going to connect the center of the circle to that midpoint and continue it on to the side of the circle. So point D is on the circle. That means CD is a what? It is a radius, right? Anytime you have a segment representing the distance from the center to a point on the circle, that is a radius. And our radius is going through the midpoint of that chord. So we're going to measure those angles. And so you can see the measure of angle AMC and the measure of angle BMC both appear to be 90 degrees. So it appears that this radius CD and this chord AB are perpendicular to each other because they form 90-degree angles. So that is question number 1 on your notes. What appears to be true about radius segment CD and chord segment AB? You are going to say they appear to be perpendicular. So we will write that as segment CD. Remember, the upside down T is the perpendicular symbol to segment AB. Make sure you use the segment bars. Remember, it wouldn't make sense to say numbers are perpendicular, and when you leave the segment bar off, that's exactly what you're talking about, a measure, which is a number. So those segment bars are definitely needed. Okay, so we're going to look again at circle C. We again have the same chord, segment AB, on that circle C. And we are going to use a 90-degree corner of a sheet of paper. It's an index card. And we're going to slide it until it goes through the center. So now we have created a 90-degree angle with this segment that goes through the center of the circle. We're going to draw that segment and again continue it on to the circle. And when we created that 90-degree angle, this radius goes through the midpoint of that chord. So number 2 on your notes says what appears to be true about segments AM and MB. They appear to be congruent. So again, we will write that as segment AM is congruent to segment MB. Remember, you wouldn't use an equal sign here. Numbers are equal, figures are congruent. So we use the congruent symbol. So let's look at question 3. Does it appear that these two relationships between a radius and a chord are equivalent? So we're going to state the second conjecture we're making with chords, and this is on your notes as well, number 3. So a radius of a circle does what to a chord? So what did the radius do to the circle? Remember, it cut it in half. It went through its midpoint, and we have a word for that. It's called bisects. So a radius of a circle bisects a chord if and only if the radius is what to the chord? Remember, it had to create a right angle. And so two segments that create a right angle are called perpendicular. So this is our second conjecture. This is number 3 in your notes. It says a radius of a circle bisects a chord if and only if the radius is perpendicular to that chord. Now remember, we've talked about this phrase if and only if several times. That makes this a biconditional statement, and it means that you can read it both ways and it's true. So a radius of a circle bisects a chord if it's perpendicular to the chord, and if the radius is perpendicular to the chord, then it bisects the chord. So you can read it both ways and make a true statement. So we're going to prove both ways. Since it's a biconditional statement, we have to prove it both directions. So question 4 on your notes is proving that if the radius is perpendicular to the chord, then it is also bisecting the chord. So the proof states that suppose that segment CD, which is our radius, is perpendicular to segment AB, which is our chord. Then we would know that triangles ACM and CMB are both what type of triangles? Well, remember, perpendicular segments create what type of angles? 90-degree angles. So both of these angles at vertex M would have to be 90 degrees, which means we could classify these triangles as being right triangles. The second part says, by what? How do I know it's a right triangle? Well, sometimes we get stuck on these, and these are really the easy ones. That's just the definition of what a right triangle is. It's a triangle that contains a right angle. So since we knew it contained a right angle, we knew it was a right triangle. The next step says we know segment CM is congruent to itself. Remember, we have a property that states that. And the reason why we know that segment CM is congruent to itself is the reflexive property. So I could mark this information, and I should be marking that as I go along, the fact that this is a right angle on both sides. And I know now that CM is congruent to itself and that CA is congruent to CB is what the next thing we're proving. So the next step says CA is congruent to CB by what? Well, CA and CB are both what parts of the circle? They start at the center and go to a point on the circle. So those are called radii. And remember, all the radii in a circle will be congruent to each other. And that is just by the definition of a circle. A circle is the set of all points that are a given distance from the center. And that given distance is the radius. So now that we have our information marked on our figure, we'll be able to tell which shortcut we're using to say the triangles are congruent. Some of you forget to mark your figures and then you miss the shortcut that is the reason why the triangles are congruent. So it's really important that you mark the things that are in your proof so you know what to give for an answer here. So if you notice, we have the right angles marked and we have two sides. Now notice the angle is not between the two sides. So this is not SAS. This would actually be SSA, which is a cuss word backwards. That is not one of our shortcuts. It only works for right triangles, and we don't call it SSA. We call it what? We call it hypotenuse leg, or HL. The hypotenuses are congruent, and this leg pair are congruent. So these two triangles are congruent by HL. Once we prove triangles are congruent, remember all of the corresponding parts are congruent. So almost always after proving triangles are congruent, we will use this same step every single time, or the same reasoning. The reason why I know AM and MB are congruent is because they are corresponding parts of these congruent triangles. So remember, we have an acronym for that. It's called CPCTC. Corresponding parts of congruent triangles are congruent. AM and MB are those corresponding parts. So that shows us that we know that segment CD bisects segment AB. If it creates congruent parts, it's a bisector, and that's just by the definition of what a bisector is. So we have proved the first part. So let's look in your notes what you should have on that. It says, complete the following condition statement. This is the first statement you must prove. If a radius is perpendicular to the chord, then it bisects that chord. That's what we're trying to prove first. So we said, suppose that CD is perpendicular to AB. That created right angles, so we knew these two triangles were right triangles by the definition of what a right triangle is. We knew CM and CM are congruent by the reflexive property. And CA and CB were congruent by the definition of a circle. Those were radii of that circle. We knew the two triangles were therefore congruent by the HL shortcut. And so these segments were congruent by CPCTC, which showed that CD was indeed a segment bisector. We created those congruent parts by the definition of a bisector. So hopefully you have those filled out in your notes. All right, so now we're going to look at the second part of the biconditional statement. In the second part, we're going to prove, sorry about that, the bell rang. So the second statement we're trying to prove is that if a radius bisects a chord, then it is also perpendicular to the chord. So it says, suppose segment CD bisects segment AB. That's the given part. Then we know that segment AM is congruent to what? Well, by definition of a bisector, we know it's cutting segment AB in half. So segment AM would be congruent to segment MB. That's the first blank on your notes, segment MB. And again, that's by definition of a bisector. That's just what a bisector does, creates congruent parts. Step 3 says we know CM is congruent to segment CM, again, by the reflexive property. So that would be your next blank on your notes, reflexive property. And we know CA and CB are congruent segments. Again, those are radii of the circle, so we know they're congruent by the definition of a circle. Remember, a circle is a set of all points equidistant from a given point. The given point is the center, the given distance is the radius. So now we know the triangles are congruent. Let's mark what we have said is true in our proof. We said AM and MB were congruent. We said CM is congruent to itself. And we said CA is congruent to CB. So we have marked our figure with the parts that are in our proof, and that allows us to see which shortcut we used. So we have all three sides of this triangle congruent to all three sides of this triangle, so they are congruent by SSS. Remember, almost always following proving triangles congruent, we're going to be using CPCTC to say corresponding parts are congruent. So angle CMA would be congruent to what angle over here? That would have to be CMB. That's the corresponding part. Angle CMB. The next statement says because the exterior sides of these angles form a straight line, that means they have to be what type of angle? They are what? They are supplementary. They have to add to 180, right? If they make a straight angle, they have to add to 180. So they are what type of angles? Well, if they're congruent and add to 180, they would have to each be 90 degrees or right angles. So we have supplementary and right. So since these are right angles, we know by definition of a perpendicular relationship there that CD is perpendicular to segment AB. And again, that's just by definition of what perpendicular means. All right, in the next video, we'll continue.